and welcome all the faculty member for this JNU pair workshop. You know the purpose of this workshop, so we have to join hands so that we can have some joint publication. We may be different, we may be doing some different research, but collaboration is always possible. So we have to just make a bridge so that JNU and all other universities can have joint publication and we can meet the milestone of our pair grant. So with this, so I am going to talk about one of my research area in detail and some other area of research as a glimpse. Okay, so if you think that we can have any overlap in our research area, so you can join our research group at School of Physical Sciences, JNU. Okay, it's better now. So you can focus me? Fine, so you are in the land of JNU? Fine, so where the research flows in the air of this university. We are mainly research university, right? And today I am going to give you the one glimpse of density functional theory, that is a theoretical tool which is needed for novel material discovery. So we will touch something about on history and background of density functional theory, then the fundamental of density functional theory, some DFT code. We will just see the list of the DFT code. So we will, whenever we are going to run any particular software for DFT, so we need some input file and what is the execution command, and then what will be the output file and how to analyze those output file. Okay, so so we'll try to give you the glimpse of these ones for two computational code. That is one is Win2K and second is WASP. And I will try to convince you that okay, DFT is good whenever we are going to produce some experimental research results, and some other area of research I will try to introduce. That will be an experimental area. So I have been asked to give the theoretical talk. So that's why I am giving for DFT. Okay, so coming to the history, so it was the Thomas Fermi model which came into picture in 1920, which imagined that okay, density can be taken as a variable in defining the many body problem. Then in 1928, Hatry method comes into the picture, which has given us the potential, but in that potential there was no exchange term. In 1930, then this potential was modified so that we are having now Hatry-Fock method, in which the exchange term was there, but an important part of the potential, that is correlation term, was missing. Finally, in the DFT, when the Hohenberg and Cohen have written a paper in 1964, which gives the existence of exact density functional, so it take into account both the term exchange as well as correlation. Exchange means the electrons are identical particle, so two electrons can exchange their position, fine, by themselves, and in the same way, so correlation means so they have to move in the presence of the other, so they cannot ignore the presence of the other electron. Suppose you are focusing on one electron, the one electron cannot move as the potential of the other electron, fine. So then this approach was computationally designed by Cohen and Shah in 1965. Then a computational approach was there. So now the density functional problem can be solved on the computers as well. And then in 1970s and early 80s, DFT became very much successful. So it was able to produce whatever the experimental result of any materials we are having. So the people initially started for the bulk materials, like any crystal structure, and then now we are moved into the nanomaterials also, whether it is even it is quantum dots or core shell nanoparticles, so we can simulate anything. So just imagine, so Walter Cohen has been given a Nobel Prize in 1998 for the discovery of density functional theory. See, so this is the fundamental Hamiltonian, which is a big one, which is containing the kinetic energy terms and the potential energy term. First two are the kinetic energy term related to electron and the nuclei, and then we are having the electron-electron interaction, nuclear-nuclear interaction, and electron-nuclear interaction. So based upon these three interactions, we are having the last three terms. Okay, so if we have to write the Schrodinger wave equation, this is nothing but SI is equal to E psi, very fundamental equation in physics or quantum mechanics, you can say. Then Bohr-Oppenheimer approximation came into picture at the very first instance, which said that nucleus are very much heavier as compared to electrons. So their motion is not possible, but only electron can have the motion. So we can neglect the kinetic energy of nucleus. So we can just ignore the second terms, you can say, and in this one, so kinetic energy is ignored, and then our this Hamiltonian is modified, and so we are having the main portion of Hamiltonian is coming from the electrons in this way. So that's why we are writing here E electron psi electron is equal to E electron psi electron. Electronic and nuclear degree has been decoupled with this approximation, but it is not taking into account any correlated dynamics of the ions and the electrons. Okay, so these are the same method whatever I have introduced as a chronological step in my first step. So first slide. So this is the Hetry method, so which says that total wave function should be the product of single electron wave function, and we are having this as our Schrodinger wave equation, that is minus 1 by 2 del square V ionic and plus VH psi I is equal to EI psi I, means this is for the ith electron, you can say. So here we are not including any exchange and the correlation term. Fine, so we are not including any exchange and correlation term. So now look at the Hetry-Fock method, so in which we have included one more term, that is Vx. Okay, so exchange term has been included, so but correlation term was not there. So if we are trying to, what it will give it whenever we solve this particular equation, what it is giving to us, so it is giving us kinetic energy and eigenfunction and eigenvalue, right? So that is EI and psi I we are getting from here. So if we are this means ground state we can found. So if we can found the ground state, so this means any physical property can be found. But whenever we are going to compare our experimental result with our this theoretical results, so what we see that there is a large deviation. So this means this Hetry-Fock method is not perfect. So that's why we have to go with some other approach. So then the one beautiful approach came into existence was density functional theory. So what it says that, okay, it is possible to convert many body problem into the one body problem. And how it is possible? So if we just imagine the unit volume is containing Avogadro number of particles. This means 10^23 number of particle. So if we say one atom is containing one electron, so this means 10^23 number of electrons are there in a unit volume. And if you have to simulate this particular volume, so we need a combination of 10^23 number of electrons and 3n variable, where n is 10^23. Just imagine, so this is a very big combination, and to design such type of the wave function is not practically possible. So then it was thought that it is possible to replace this wave function by some simpler quantity. And because this earlier approach was very complex and numerically time demanding, so the new approach which have converted many body problem into one body problem is density functional theory. So see, so that's what I have explained. So a solid is described by the wave function of all the atoms, and if we say that we are having one electron per atom, so this means 10^23 electrons will be there, and combining all these electrons is practically impossible. So then we have to describe the single electron in the mean field of atom and the other electrons. So the main idea in the density functional theory is that we have to describe the many body system by using functional. Fine. When I say functional is different from function, right? E is a functional of rho, where we are writing in the square bracket, not in the small bracket. Like suppose I say psi x, psi is a function of x, right? This means it is containing the the expression in terms of x. But when I say E is a functional of rho, so whatever the expression of E will be there, so psi will not, rho will not be there in that expression. Means you have tried to check the energy for entire range of rho, right? So means it is an integration term. So rho will not be there. So that's why it is a functional. So okay, so now, so as rho, this density can depend upon the three direction. So that density can be in a, suppose we are having an isotropic material, so density can be different in x direction, y direction and z direction. So if it is so, so then density can depend upon the x coordinate, y coordinate and z coordinate. So this means we need only three variable, not the 3n variable. So this means while using the density function theory, we have converted 3n degree of freedom into 3 degree of freedom. So now the problem is very simpler. So knowledge of density is sufficient for complete determination of all the ground state properties of the atom or crystal, right? So these are the two theorems which describe or made the basis of the density function theory. The external potential Vr is a unique functional of electron density, means you can have one-to-one mapping, and the true ground state energy of any many body system is a unique function of density. I am writing here n, that is same thing rho. So E is a function of n, and the second one says that now okay, so it was said that energy is a functional of density. Then how can we find the ground state energy? Ground state energy should be the minimum energy. So it can be found that true ground state energy is that which minimize the total energy, or E0 is equal to minimum of E. And in this way, suppose for this we need N0 R is the density, so this will be our ground state energy, right? So these two theorems, that is Hornberg-Cohen theorem, constitute the basis of the density function theory, but it is not offering any way of the computing. Means okay, so we are having a theoretical tool, but how to map that one in a computational architecture, so it is not there. Okay, so let us try to understand the concept with this particular slide. So how the density function theory is changing 3n degree of variable into 3 variable only, and how easily we can solve the problem. So we are having these two problems. One is this problem, second is this problem. Imagine, so I am just okay, so imagining, so we are having 3n number of variable. As a representative, I am taking 1, 2, 3, 4, 5, 6. 6 number of electrons. So one electron can interact with this. Okay. So in the same way, second electron can also interact with all these ones. So means whenever you are writing the potentials, you have to write the interaction term for each and every electron interacting with the other ones, right? So this means you are having an interacting electrons plus real potential, means that potential which will go on all these interaction will be there. And for this, definitely you need 3n number of variable. And suppose if it is 6 electron, this means 18 number of variable, fine? Okay, so now what we are just trying to imagining, so we are having, suppose these 6 electron are as it is, but these are not interacting. We are saying that these are non-interacting fictitious particle, and the potential, whatever the potential was there, which was seen whenever these electrons were interacting, right? So we are imagining that is nothing but my effective potential. So we are adding the non-fictitious particle or electron with the effective potential, which can go on all these interaction, right? So this means if electrons are not interacting, so this means our problem is solved, right? So we need in this case the only 3 degree of freedom, right? So non-interacting Cohen-Cham electrons lives in the external potential, right, such that their density is same as fully interacting density, fine? So in this way, by just this problem is complicated and not easy to solve, but this is easy to solve. So this is the beauty of the density function theory, that we are going to have the result from this particular approach, not by this particular approach, but the result is almost same, right? So now we are defining the V effective as the this potential, where we are having the this three some of these 3 potential is known as Cohen-Cham potential, where this VH is nothing but my Hartree potential, and this is my exchange correlation potential, fine, and this is my external potential. Okay, so now what is the relation between this density and the wave function? So you can have the one-to-one relation from wave function to density, that is you are taking the help of all the electrons, whatever is there. Suppose n number of electrons are there, So you have to take the square of the wave function related to one particular electron, and you're going to sum those ones, right? So then in analogy of the Hatry methods, so like we are having a equation in the Hatry method, so we are having the same thing here, right? So h cross square upon 2m del square plus V effective. So here we are having Hatry potential. Now we are having V effective, right? So psi I is equal to EI phi I, and this is my Cohen-Charm energy, or ground. You can find the ground state energy with this one. This is Cohen-Charm orbital or wave function, and this Cohen-Charm equation reduces many body problem into the one body problem, right? Okay, so so this means we have to focus on. Let me go to the previous one. So this is the exchange correlation potential. So we need the approximation for this one, exchange correlation potential. So for each and every calculations, we have to just imagine what will be the value of this exchange correlation potential. And if you can just go for the good exchange correlation functional or potential, then you can have the true ground state energy. So this is the approach. As I said that Cohen and Charm has given 1 year after the discovery of these two theorems of density function theory a computational approach where we can have an iterative method so that we can have the self consistency. Let us see in this one. So this is self consistency density functional calculation. We have to guess the electron density, and then we are going to compute the effective potential. Fine. So this effective potential is inserted here, and then with the help of this we can find what is the psi. So if psi is known, then we can find one more electron density. So now we are going to compare this electron density with this electron density. So if these are same, so this means we have obtained the self consistency. If these are not same, then it will be our new guess. Then this cycle will be repeated until unless we are going to achieve the convergence. So when convergence is achieved, so this means we are getting the ground state energy. Okay. So don't think that whatever I have given you, so this is a totally theoretical concept, and we are not having any knowledge, because I am just talking about the wave functions and some complicated things. So, but I will make your life easy with these slides. So what I am writing, running DFT package is driving a car, and everyone is expert in car. But if I ask a question, do you know the internal mechanism of car? Everyone will say no. Fine. But you know ABC. Right? ABC means accelerator, brake and clutch. And you know fuel is there in the car, and you know traffic rule. In Indian road you have to move on the left side, right? And so understanding the basic concept that can control the car, so this means you are very good driver, right? And speeding time in driving depends upon variety of the road condition. What is the road condition? If you are in Delhi traffic, means 10 kilometer you will cover maybe in 40 minutes. But if you are in Jaipur highway, so 10 kilometer you may cover in 8 minutes or 9 minutes, right? So without knowing the much technical detail, how the fuel injector work, radiator work, you can cross down the town, right? You can cross down the town, fine, whether it is Delhi or Jaipur or any highway. But if you have to build a new car, this means you know the internal mechanism of the car. Only then you can build the better car, right? Let us now think the same thing for DFT. Okay, understanding the basic concept of the running the DFT package, that what is the, how you make the input file, what is your execution command, you can obtain the output files. Yes or no? Yes. And it totally depends upon what type of calculation you are doing. Whether it is for bulk material, maybe suppose you are trying to calculate the band structure of silicon, or you are just trying to calculate the magnetic moment of iron. So that is very simple calculation. Maybe it may be run within 1 minute. But suppose if I say you have to do it for a graphene monolayer, or some adsorption in the graphene monolayer, so this means you need a lot of time. Okay, so means spending time in the running a DFT package, it totally depend upon what type of your problem is, whether it is simple or complex. Same thing, road is simple or the complex, fine. So and so if you know the input file, you know how to execute after making the input file, how to execute the DFT package, you can obtain the output file. So this means there is no technical detail is involved, no wave function is involved. If you are running, if you are experimentalist and you just want to take the applied aspect of the density function theory, you can take it. No problem. Fine. So you can learn the DFT package within 15 days. It's not a big issue. You are having a PhD, you are having some PhD student, you can ask them to learn. 15 days they will run. You can send them to one expert, maybe anywhere in India or abroad, and they can run and can do the calculation for you. Again the same thing. So if you have to build a new DFT code, you must know how the previous code is written. You have to go in the deep. So in the same way. So this means we are just trying to correlate that DFT package is just simply running the car. Imagine this is you in future, and if you are using DFT just now also, so you are you at present also. Fine. So sitting on your simple at home or at your office, you can run any of the DFT, any of the physical properties, just like magnetism, band structure, mechanical property. You can do any of the defect engineering, substitution, vacancy, dislocation, adsorption, doping, interstitial effect, nanomaterial, anyone you can simulate, transport property, optoelectronic, and non-linear optics. So you can cover each and everything, any physical property you can cover. Fine, you can just check whether the new compound, if you are designing a new compound, whether it is feasible or not. If feasible, in which phase it is feasible. If feasible in a particular phase, whether it is metallic or magnetic or not. Anything you can compute, and in this way you can design the novel material. Right. So these are some of the DFT code. Hopefully some of these are known to you. So based upon the local orbital basis code, we are having Quest, Siesta, ATK, Crystal, Empirio, and FHI, AMs, and so on. And the augmented methods, all electron, where we are treating the different electron differently. SP, DF, all electron differently. So we are having some all electron codes like ELK, exciting, fluor, RSPT, and Win2K. We can have the plane wave and related codes where we are going to use the pseudo potential, because pseudo potential is easy to simulate. VAST, CASTOP, CPMD, ABNet, Big DFT, and so on. So many codes are there depending upon type of your problem. So you take the help of any of these codes. And if you are in biological sector or chemist, so you can go for the molecular code like Gaussian and NWChem, Octopus, DMOL3, and so on. So many codes are there, so you can just check what type of problem you are having. Okay, suppose you are having any particular research area in which you are working. Just check whether DFT can help in your research area. If yes, then search more, try to check the similar paper, and try to reproduce those ones also. If you can reproduce the previously published paper, then definitely you can go for the new one also. Okay, so as I have to make your interest, so I will try to give you the glimpse of the input file of two codes, that how to design the input file, and you will see that if you are just following me, then you will see that these are not a big thing. So you can easily grab these ones, right? So Win2K, that is all electron code, where we are treating the different electron differently. Win full potential code we are having here, and one I will give you for the pseudo potential, right? So Win2K, so this is a software package which is originated from Vienna Institute of Technology, Vienna, Austria, and it is the commercial one, means you have to pay some of the amount for this, but for academic purpose it's not a big amount. You can easily purchase this one. So it is based upon full potential linear augmented plane wave methods, and in this unit cell is divided in two portions, 1 and 2. One is that where actual atom is there. Second means it is an interstitial position where no atom is there. Fine. So we will have the different type of the wave function for the reason 1 and different type of wave function for the reason 2. For reason 1, so we will have the basis function are a spherical harmonic radial wave function, where we are taking help of not only plane wave but the derivative of the plane wave also. But if it is interstitial space, because in the interstitial space electron is not bound, it can move freely, right? So we need only for the free electron we need only the plane wave. So that's why e raised to power eta k dot r is there, right? So here we are having plane wave, here we are having the augmented wave. So that's why it is augmented, means one term is mixed with the derivative of this first term, right? So this is one particular software which is written in Fortran, and a number of programs are there, all are linked with the C shell scripts. So what you have to do, you have to make a particular directory. Fine. Suppose the directory is name is case. Okay, suppose you are running for iron FE, so your directive will be FE. So in general I am saying case, and then you will make a master input file. That is, that name of that file will be case.struct. If it is iron, it will be fe.struct, right? And then you will initialize the calculation by INIT_LAPW. Then, so this is your first command, fine. So first you have to design the master input file. Then these are your execution. These are the two execution command. INIT_LAPW, run_LAPW. And if it is a magnetic system, then instead of run, it will be run SV. SV means spin polarization, right? So you can run Win2K from the graphical user interface also. GUI is also there. That is called W2 Web. And but you are advanced user, then you can do it on the terminal window or console also. Okay, input, output and SCF file. So all will be stored in this particular directory, and you can identify these ones by just knowing whether what type of extension is there. For example, IN2, IN1, this type of files will be there. So IN means input file, right? So if it is output 1, output 2, output SO, so all will be the output file. And if it is the for the iterative cycle, so it will be just like SCF0, SCF1, SCF2, right? So you can identify all these things. And so as we have to make the master input file, so we can design it with the help of structure generation of graphical user interface tool, that is W2 Web, and then we can perform the INIT_LAPW, right? So just see how easy is this one. So right hand side, so I am just giving you one particular box in which you will make the input file. What you need to know in order to design the input file? You must know what is your crystal structure. For example, here I am taking the help of TIC, right? In TIC you are having two atoms, Ti and C. You must know what is the lattice parameter of TIC. That is, in this case is this one, 4.3, 4.3, 4.3. What is its angle? Alpha, beta, gamma, all 90. And where Ti is present, for example, Ti is present at 0, 0, 0, and C is present at 1 by 2, 1 by 2, 1 by 2 in the unit cell. So and what is its lattice type, whether it is BCC, FCC or anything else. And if you know this space group also, you can also select this space group from this list. Okay, by just knowing this one, if you just click on this save structure, so this means you have designed your master input file. As I have taken the help of the TIC, in the same way you can design for any other things also. Like FE you can design. So FE you will have only one atom, right? So you can just write the FE, and you can just put that here BCC, and lattice parameter you can put whatever it is. Okay, 2.87 angstrom I think. You can put it here, same thing. So only one atom, and then save. FE structure file will be generated. You can just, whenever this will be saved, so suppose this is TIC, so what will be this file? TIC.struct, right? And this TIC.struct, you can visualize this one in the visualization tool, right? We are having some visualization tool. For example, I think you have heard about Vesta. Vesta is a software in which you can just check what type of input file you are having, right? So you can just check, okay, so whether I have designed my input file correctly or not. You can just check this one, fine. So if you have designed this particular file, okay, after that you can just go for INIT_LAPW, and you can do all the things from this graphical user interface also. Just click on this one, initialize calculation. That is the second step. After making this structure generation, save structure, initialize calculation, and then run SCF, run_LAPW. And finally you can go for the task, and you can find any of these physical property like electron band structure, density functional theory, density of state, electron density plot, X-ray spectra and optics, all the optical properties, excited state properties you can find, right? So it is step-by-step initialization, and you can learn more. And for any computational tool, the online help is available, so you can just Google more, or you can look on the YouTube also. Okay, so as I have given you the glimpse for one particular code, now let us focus on the second one, that is VASP. It is more famous because it takes less time. Why it is taking less time, I will explain. Okay, so VASP simulation package, so it is also originated from Austria, but from a different university, that is University of Vienna. Okay, so density functional theory is implemented in this particular computational code. And what is the beauty? So instead of using the actual wave function, like we are taking the actual wave function and actual potential, we are taking pseudo potential and pseudo wave function. So these are my actual potential. This actual potential, but this is my pseudo potential. This is my actual wave function, but this is my pseudo potential. Okay. So my actual wave function is this having the harmonic step. Fine. But this is smooth. This is just like Gaussian wave function, right? But so just imagine this particular vertical line. So here I have written RC. RC means critical radius. So, and this is the R is nothing but the distance of the electron from the nucleus. Means this is the nucleus position. And as soon as you are going away from the nucleus, so this means you are approaching towards the valence electron. And after the RC, you will find the valence electron, right? Or semi-core electrons are also. It means the outermost shell and the second outermost shell electron. Okay, so outermost shell electron are generally called valence electron, and second outermost shell electron are called semi-core electron. Maximum you need only these two in order to explain any ground state property, right? But after the critical radius, just imagine, so this pseudo potential and actual potential, these are same, these are overlapping. Or pseudo wave function and pseudo actual wave function are same. So means it doesn't matter if you are explaining the ground state properties whether you are taking the actual or pseudo potential or wave function. Means you can take the help of pseudo potential and pseudo wave function also. And what is the advantage of taking the pseudo things? Because with the help of pseudo, so you can save some computational time. Means the calculation will be taking less time as in the case of the actual or true potential and wave function. So that's why we take the help of pseudo potential in case of VASP. And the one method in which we can define the pseudo potential is projected augmented wave method. It transforms rapidly oscillating wave function into smooth wave function, which are more computationally efficient. That's what I have explained. Okay, so VASP has been implemented in all the first principle calculation for all the cases, whether it is bulk or nanomaterials. Like in Win2K, I have explained that we need only one input file. So here we need 4 input file, right? You have to design 4 input file, and these 4 input file are in-car, post-car, port-car and K-point, right? So when we are going to just check what is in-car, why this type of name is there. In-car means input card. It is small acronym, input card. In means input, car means card. Like you are having the playing card, so you need only 4 per card to play this game, right? And what will be this in-car? So here some input parameters will be there. And this post-car means post means position, card. So it is a card which contains the information about the position. Like TIC, we have taken the help of TIC in order to explain the, in Win2K we have tried to explain how we will design the input file for TIC. So in TIC, TI is present 000, C is present at 1/2. So this type of information will be there in post-car file, right? And then port-car, as I said, we will take the help of the pseudo potential, which will be already available to you. Means your program is not trying to calculate the pseudo potential, actual potential. So pseudo potential is defined already for all the atoms. So whatever is your unit cell, suppose it is TIC, so you need the pseudo potential of TI and C. So you can take from the repository and you can design the port car with the help of that one. And this particular file will contain the information about the pseudo potential as well as the exchange correlation potential. And finally, as you have to run this calculation in reciprocal lattice space, so you have to define a K-point mesh. Fine, so that you can have a sufficient number of electrons to have the desired calculation or results. First one is the control one, and this is position, this is potential, and this is just for defining the unit cell. Okay, so then you can take the help of execution command. Like the execution command, there was init_lapw and then run_lapw. Here the execution command will be wasp_std. std means standard calculation of wasp, where you can first relax the calculation right? And then you go for the SCF run so that you can have the self consistency, and finally you go for the 1 point calculation for any physical properties. So when you go for the 1 point calculations, you are having some output files. So these output files will be having this type of the name, like count car, OZ car, out car, charge car, CHG car. So count car means corrected car, means it is the modified version of Porsche car. Okay, so you will define a Porsche car, fine, and definitely you may have some disordered lattice, right, and you have given the position to various atoms, but in the equilibrium condition, the position of these atoms may be changed. So whatever is the change in the position, that will be contained in the count car file. Okay, so you can say that for the next calculation, when you are going for 1 point calculation or SCF calculation, you take the help of this count car and you convert this count car into Porsche car, means it will be your new Porsche car for the second calculation whenever you are going for the SCF as well as 1 point calculation. OZ car, it tells you that how many electronic and ionic step has been taken care in order to have the consistency, self consistency. Then out car, so it is giving you the complete output of run, including input file data as well, and charge density is stored in this CHG car, right? So by just knowing how to design the file and then how to execute the file, you can obtain this type of the output file. And then what is theoretical physics or theoretical research? Extract the understanding or extract the physics. So I am from physics, so extract physics from the number. Fine, so whatever you will do from these files. Okay, so as you just imagine, so whatever we are doing, so we are doing in numbers. So but we need some visualization also. Visualization tools are these one. Hopefully some of these are known to you, and most famous is this Vesta. XPython generally is used in Win2K. Vesta can be used for any particular code. VMD, Ovito, Crystal Maker, P4 VAS. So okay, so some are the free ones, some are the paid one. For example, Crystal Maker is paid one, and Vesta, P4 VAS, XResident, so all these are free, right? So just imagine, so these days, don't think that we are just doing the simple calculation. So it is of no use. Everyone has done this one in the last century, means in the period from 1980 to 2000. All the bulk materials have been discovered and chapter is closed. But now, at present, what we are doing, so we are going for the reduced dimensionality, means 1 dimensional, 2 dimensional, 0 dimension. Not only this, that is also somewhat saturated. These days, in 2018, so van der Waals heterostructure has been designed, where you can design a heterostructure of two different 2D materials, and from this heterostructure you can take the property of both materials. Fine. So for example, if you are having a heterostructure of graphene and MOST, fine. So by just taking the help of this heterostructure, you can withdraw the property of graphene as well as MOS2. So that's why people are more focusing on not only 2D material but on 2D heterostructure or heterojunction, right? So and you can design these heterostructure using the Vesta, right? So here you are having a, suppose one input file for graphene, one input file suppose for hematine. What is this hematine? Hematine is just similar to graphene. Like graphene is exfoliated from graphite. In the same way, hematine has been exfoliated from hematite, that is the iron ore, right? So this is 2D material, this is also 2D material. So if you can place one over above like this or like this is side view, this is top view, fine. So top view, one over the other, so it means here picture has been taken from here, and side view means the picture has been taken from here. So this is my side view and this is my top view, right? So there is a vacuum, fine. So that's why it is a van der Waals material. Okay, same you can design for other two materials. For example, here I have taken the help of graphene hematine, or it can be graphene MOS2 or graphene chromia also. Chromia means Cr2O3, right? Okay, so but how we can design this one? That is also a crucial point. So we have to take the help of suitable supercell. Unit cell everyone know. Fine, supercell means you have to repeat the unit cell. For example, if it is 2D material, so you can repeat your unit cell in 2 direction only, not in the 3rd direction, so that you are having a complete monolayer like graphene is there, right? So suppose this is my unit cell, and this has been repeated in the x direction, this has been repeated in the y direction. Okay, so you are having only xy plane. In the same way, Hamilton is there, so it has been repeated only in x and y direction. Right, so okay, AB I am writing, that is the same thing, xy plane. Okay, so how we take the help? So suppose we have to design this one. If it is a 2D material, this means you will design material like 221, 331, 441, 551, means 5 time in x, 5 time in y, but 1 time only in z, right? So whatever is your unit cell, that is not now known as the supercell. So you take the help of one particular supercell you will design for this, another supercell you will design for this, in such a way that you are having the minimum lattice mismatch. Suppose 12 angstrom is the unit lattice parameter for this, same should be for this one also. It can be 12.1, 12.2. So you have to just search a supercell in such a way that the lattice parameter is almost same for both the individual layer. Okay, so it totally depends upon what is the nature of these materials. We can have a different supercell for these two supercell. For example, suppose it may be here 221, it may be here 331. Anything you can just take it. And then when you design this particular file, so you go for the relaxation and then the convergence test, so that you can just correct this vacuum thickness. And definitely you, in the starting, you just take the 20 angstrom, it may be coming out to be in the relaxed geometry, it can come out to be 15 angstrom, 17 angstrom, whatever it is. Okay, so I have tried to give you that why this theoretical research is so much important, and now this is the main important. So if you are experimentalist, now it is a trend to go from wet lab to the dry lab, means the maximum trial we should run on the computer, so that there is no need to perform the actual experiment for those configurations which are not desired, means which will be neglected after the optimized result. Means we can reduce the experimental trial with this. Wet lab use is limited. All the trial can be performed using the simulation on the computers, and then you can select the desired configuration, go for the experiment. Just imagine what I am saying. So suppose you are having an alloy of AB, A and B, and you don't know what is the composition of A and B in the actual alloy. A, X, B, Y you are having. What is the value of X and Y you don't know. If you are experimentalist, what you will do? Okay, so you will take, for example, 20 number of combination of X and Y. Maybe 10% of X, 90% of Y, then 20% of X, 80% of Y, and so on. Okay, and then you will run the experiment for all the 20 configuration, right? And then you will analyze your result, and you will say that, okay, out of 20, one configuration is coming best for me, and I should use it for the further experimental analysis, right? But same result is coming from the theory. So why it is not possible that you can design the 20 experiment on computers, then you select the desired configuration and you perform the experiment only for the one configuration. So in this way, you can just, within this example, you can just save your 19 experiments, right? So means you have no need to design the 19 experiments, only one experiment is sufficient. Out of 20, 19 is done on the computers, right? Okay, so this is the beauty. Okay, so now I am trying to show you some of the 3 results I am going to show you, then I will come to the other area. So other area I will rush through, but these ones, so just to convince you that these results are really giving you some discovery of novel materials, so that we can have a discussion on these ones. So 2D materials and heterostructures. So why it is necessary? Because we have to design the nanomaterial for the magnetic application, and prediction of the magnetic alloy. So that what is in the magnetic alloy, what is the magnetic phase of the alloy composition? We can analyze this one, because whenever experimentalists found new things, okay, suppose one magnetic phase is there and experimentalist is not having the idea what type of interactions are there, based upon that particular phase is arising. So that can be solved, this problem can be solved with the help of density function theory by just explaining that which states are responsible. Then accordingly mechanism can be set for this one. Okay, so then in the solar cells, we can take the simulate any particular. Solar cell is a device, fine, but solar cell is made up of 1, 2, 3 materials depending upon what type of solar cell you are having. For example, if you are having the perovskite solar cell, hybrid halide perovskite solar cell. So it is PIN configuration, P-type, intrinsic and N-type configuration, or electron hole pair, electron transport layer, hole transport layer and absorber layer. Means 3 different materials are there. Okay, individually you can study all these materials, because DFT can give you the result for the materials, not for the device. Okay, so you can just check the electron transport layer, whether it is suitable for perovskite solar cell, and these are important because in future, so all the silicon cell will be replaced by this perovskite solar cell, as they are having the enhanced efficiencies. Okay, so coming to the first one, that is the 2D materials and heterostructures. So just see that this is the hematine, that is the 2D alloy of 2D materials coming from the hematite ore, right? So hematine is more far-reaching, ultra-thin magnetic indirect band gap semiconductors, because this has been discovered from experimental side also. So we try to just check what will be its Curie temperature. So we have designed this one, right? So like from the graphite we can design graphene, and in the same way from hematite we can design this hematine. Okay, so the only difference is that it is 1 atom thick and it is 3 atom thick. Still we can consider it as a monolayer, right? So, and we have obtained the Curie temperature for this one, and for the 2D materials, so Curie temperature is generally not coming at the room temperature, but it is coming out to be more than room temperature. So just see that here. So, and with the help of strain, so this is the pristine one, 295 Kelvin is there, and so as you are going to apply the positive and a negative strain, so the TC remains almost near to the room temperature, you can say, and the magnitude of the magnetocrystalline anisotropy and magnetic moment increases with the compressive strain, means it is going to increase, right? Okay, so just imagine, so this is going to increase. Fine, so from theory point of view, what we have tried to understand, so in the report it was said that it is a ferrimagnetic material, right? And in the unit cell of hematine, so we are having 2 type of the Fe atom. One is coordinated with the 6 oxygen atom and other one is coordinated with 3 oxygen atom, right? And based upon these unit cells, so we can design this spin, we can associate this spin to the both sublattice of Fe, whether it is this sky blue or red one. So if you give, okay, 2 atoms are there for first sublattice, 2 atoms are there for the second sublattice. So based upon this we can design 5 configuration, and we can just check which configuration is the most stable coming out to be. So formation energy is coming out to be minus 1.6 for this the A5 configuration, in which you have taken this Fe1 as the up and Fe2 as the down. Okay, so this way, and you are having a magnetic moment, so it is not a complete antiferromagnetic case, so that's why it is a ferrimagnetic case. If it is a antiferromagnetic, that it should be coming out to be 0. For example, here what we are taking, one is up, one is down, one is up, one is down, perfect cancellation of the magnetic moment, so that's why it is antiferromagnetic. But we will select this one. Why? Because formation energy is most negative in this particular case out of these 5. Okay, so that is also go and check in the experimental results also, that is it is ferrimagnetic, right? Then you can, as I said, that you can take the help of a 2D material in order to design the 2D heterostructure. So we can do so. So we have tried to design the graphene MOS2 heterostructure in such a way that you can extract the property of both graphene and MOS2. So what we have seen that, okay, so in whenever we design this one, still it is a weak semiconductor. But if you do one more thing, you can do the CR adsorption. Adsorption means on the surface you can place this CR atom, then weak semiconductor can be converted into metal. Fine. So and in this way you can introduce the magnetic moment in both the stable configuration. Well, if you put this CR atoms, you can put in a number of ways. and out of number of ways only 2 configurations are coming out to be stable, that is G top and S hollow. Whenever you place this CR on the top of graphene layer or hollow position of the MOS2 layer, right? So resultant absorbed heterostructure means when you are going to absorb this CR, so it is coming out to be an excellent candidate for the spintonic devices because it is the magnetic one, right? So as I said that many configurations are possible, so it may be G hollow, S hollow, G top, S top, fine. And this is my pristine one. So top view and the side view. So just imagine, so if it is hollow configuration, this means you are having a, here just you can imagine here we are having graphene ring. So if you are placing your CR atom only on the center, then it is hollow configuration, and if you are placing it on the top of any of the atoms of this hexagon, then it is a top configuration. Whether it is on graphene, so it is G top, whether it is on MOS2, it is S top. So out of these 4, only 2 are coming out to be stable, right? So which I just given in the last one, that is G top and S hollow. So G top and S hollow. So these are coming out to be stable, and based upon that you can go for the band structure analysis. Okay, so in the band structure, so what we see that, so it is converted into the, so this is a weak metal, so whenever we are going to introduce the CR, so these are going to be overlapped, and in this way, so it is coming out to be metallic as well as magnetic, right? So it is a glimpse of the 2D material and 2D heterostructure. So just imagine, so this is one of the results where we have tried to help the experimentalists in order to check whether the magnetic phase is why the one particular magnetic phase is behaving extraordinary. See here, so they are trying to design these type of the alloy, that is U2 plus X, Ni 20 minus X, B6 and so on, fine. Okay, so if you just take the X is equal to 1, then it is U3 Nb 20, fine. And if you take X is equal to 0, then U2 Ni 20 and same. In the same way here you take the X is equal to 0 or X is equal to 1, again you can have U2, one is U2 compound, one is U3 compound. In the same way you can have Nb3 and Nb2 compound, fine. So total 4 compound they have designed, right? So they have synthesized these ones, and what they have seen that, okay, out of these 2 and out of these 2 only U2 compound was stable, and out of these 2 only Nb3 compound was stable, right? So here U2 stable, here Nb3 stable. So they are not having the idea why U3 is not stable here and Nb2 is not stable here. So whenever it is Nb2, then this means Ni will be 21, right? Not only this, so when they are designing these particular magnetic phase, so they have checked that an intermediate phase can also be designed, that is Nb 2.5, Ni 20.5, B6, right? And this was coming out to be ferromagnetic, and whereas this Nb2 is coming out to be paramagnetic or non-magnetic, you can say, right? And this Nb 2.5 is coming out to be ferromagnetic. So they are not having the idea that Nb2, okay, if I focus on Nb, so Nb2 is not forming, Nb 2.5 is magnetic, and Nb3 is non-magnetic, right? So what we have done, so we have taken as it is a bulk compound, so we have taken the help of Wien-2K calculation, and we try to check that how this intermediate phase is having the magnetic moment of 0.6 Bohr magneton, right? So for this we run the fixed spin moment calculation. So we have designed the fixed magnetic moment to this particular alloy, and then we have tried to identify which states are responsible, fine. For example, so these are the density of states calculations. Okay, so upper portion is for the upspin, down portion is for the downspin, and based upon this we have tried to give them the actual explanation why it is happening that the intermediate phase, that is Nb 2.5, is coming out to be magnetic, right? And coming to this one, that U2 and Nb3 is coming out to be stable, and U3 and Nb2 is not coming out to be stable. It can be explained based on the basis of the formation energy, and if your formation energy is negative, so this means it is stable. If it is positive, then it is non-stable, fine. So for U2 and Nb3 it is coming out to be stable, but for the other case it is coming out to be positive, so that's why these are not stable. Okay, so in this way we try to explain. Last case, so this is the hybrid halide perovskite solar cell, where you are taking the help of the glass substrate, where you are going to etch and some portion will be FTO, and then you are having the electron transport layer, that is TiO2. Okay, so after that we are having the absorber layer, that is based upon the perovskite material. It can be the hybrid one, means the mixture of organic and inorganic, because inorganic gives you the stability and organic gives you the efficiency, right? Then you are having the whole transport layer. Finally you are having the metal contact. Fine. Okay, so it is the interplay of these three layers: ETL, HTL and absorber layer. You can choose any of these ETL, any of the HTL, you can choose any of the absorber layer, perovskite layer, and you can have a new solar cell, perovskite solar cell, right? So it was thought that, okay, if it is a perovskite material and light has to come from this particular direction and it has to go in the absorber layer, and all these are the transparent material, so that these can go. But this is TiO2, this is having different structure, and this is perovskite structure, it is also having different structure. So lattice mismatch is there at this surface. Fine. So it was thought that if we can take here also the perovskite materials, then this lattice mismatch or this interfacial mismatch will not be there in this structure, and electron can hop from absorber layer to this particular layer, that is electron transport layer, easily. Right. So based upon that, so what we have tried to design, so instead of taking this TiO2, we have taken the help of La-BSNO3, right? So La-BSNO3 was designed in the experiment, right? So what we have tried to show, so as I said that this should be the transparent one, so that all the light coming from to the perovskite material, light will come from this particular area. So if this is this is transmitting the light, so this means it is not, this particular layer is not absorbing the light, or it is not reflecting the light. Whenever light falls on a particular material, only three effects can take place. Light can be reflected, light can be absorbed, or light can be transmitted. Fine. So we should have 100% transmission, no reflection, no absorption. So that's what we should prove. So we have tried to prove with the help of DFT calculation. So within the optical region, absorption is coming out to be 0, reflectivity is almost 0, and so this means if absorption is 0, reflectivity is 0, what is there? Only reflection, transmission is there, right? So transmission is there. So this means this can be, this particular layer as an electron transport layer can act as transparent conducting oxide. And in order to prove whatever we are predicting that is true, so we try to just check the dielectric function. We are having the experimental data for the dielectric function. So just see that, so this is experimental data, this is theoretical data. So almost similar type of the matching is there. So we can expect that whatever the result we are predicting, that is at par with the experimental result. So, but why we are replacing this TiO2 with this particular layer? Because it can have more electron ejection and it can have large built-in potential, right, between the two layers, so that we are having interfacial mismatching less, and it can increase the electron mobility of the in the layer, right? Okay, so based upon this, so our research aspect is that we are going to touch both approach, that is wet lab as well as dry lab. Fine. So if you are a material scientist, so you can just think that you can go in the wet lab, means actual experimental lab. You can go for the experiment material synthesis, and you can go for the device fabrication also. In the same way in the dry lab, so you can go for the material modeling as well as device modeling, or device material simulation or device simulation, right? So device simulation is different, where you have to just imagine the complete device. You have to take the some governing equations by which the device is giving you the result, and based upon that we are having some numerical modeling method, and you can design the calculation for the device modeling also, right? So other area of research in which we are working are perovskite solar cell, thermoelectric material and luminescent material. Fine. So I am covering something about these ones. So perovskite solar cell, so how we are taking the help of, so these are the main step in the device fabrication of perovskite solar cell. So we have to go first for the device substrate cutting, that is FTO or ITO we are taking. Then patterning is there, masking and etching. Substrate cleaning we do. Then as it is a laboratory synthesis method, so we can go for the synthesis of the precursor solution like ETL, HTL and absorber layer. Finally, the thin film deposition, spin coater is there, right? So these are available in each and every lab. Fine. So in the pair, so we have purchased this thermal evaporator also. So okay, so we can make the thermal contact with the help of this, that we can design the electrodes, and finally with the help of solar simulator we can go for the IV measurements. Okay, so this is a glimpse that substrate cutting is there, then masking is there with the help of Kapton tape, then etching is there with the help of zinc dust and HCl. Okay, so you can have patternized surface, so that you are having the FTO only in this particular one, and otherwise all FTO is gone, it is only glass. Okay, FTO substrate, patternized substrate, then you go for the coating of first layer, then perovskite coating, spirometed coating means HTL coating, and finally the EO deposition, right? Okay, so one more cartoon. So FTO substrate, patterning with the help of Kapton tape, etching and patternized surface. Okay, you have to make the two metal contact. Fine. So first Kapton tape you have made here, so that you can have the front contact, and with the help of this Kapton tape you can grow this particular one, so this will be visible, means this FTO portion will be visible. You have to make two electrode. Fine. So when suppose this is not there and you grow 3 layers over the above, so this means FTO will be covered, but you need FTO also, so that you can have 2 electrode. You have to take the help of 2 clip, so that you can note down the current, right? So by applying this Kapton tape, you just then go for layer by layer growth of HTL, ETL and absorber layer, and finally you can deposit the metal contact here, that is known as back contact, and then you remove this Kapton tape, then this FTO will be available. So one contact you can take from here, and one contact you can take from here. Okay, so this will be a final device, and so there are the 4 steps: solid state synthesis, thin film deposition, metal contact formation, and finally the characterization. So see here, so this is actual fabricated perovskite solar cell device, and under this solar simulator, so you can take the efficiency measurement or IV measurement. See here, so as I said, you need 2 clips just to make the contact. So one you will make it here, because you have applied the Kapton tape here and then removed it. So FTO portion was available here. So with the help of this 2 electrodes, so you can note down the current electricity, right? So this is actual fabricated device which we have designed in our case, and we have taken the help of one buffer layer also, so that less degradation is there in case of our absorber layer. Only degradation issue is there in the absorber layer, so that's why we need the protection of this particular layer, and we have taken the help of the buffer layer, right? For 3%, actually we have done it for triple cation base perovskite material, and for 3% guanidinium doping, so we have got the maximum efficiency, that is 20.7 in the reverse scan. So this is for the device performance, and with the help of solar simulator you can do it. Fine. So this is very important. So whenever you are going to report some number for a device, you must ensure that your number is correct. For this, the repetition of the experiment is very much important. Fine. So you should repeat your experiment a number of times. For example, we have done it for 20 devices, and try to take all the photovoltaic parameters like VOC, JSC means full, and fill factor, and the power conversion efficiency. Okay, so your statistical variation should be very less. For example, so this for 3% we are getting the actual desired efficiency, means the maximum efficiency, and so this variation is very less, and you can report the actual efficiency as the average of all these 20 device result. Fine. So that will be your final result. So this means this statistical distribution you must know, and if this spread is more, so this means some lacuna is there in your experiment. You should repeat that experiment, right? And with the help of degradation you can check, and you can just see that with respect to reference one, if you take the 3% guanidinium doping, so degradation is relatively slower as compared to the pristine case. So that's why it is fruitful to take the 3% of guanidinium doping, right? Okay, so if you cannot have the facility, or you just don't want to design the perovskite solar cell device completely, then what you can do, you can go for the material synthesis of one particular layer, maybe ETL, HTL absorber layer, right? Or you can go for the DFT analysis of that one also, and you can club this one with the device simulation result. For example, so this is, and these days people are going for the tandem solar cell, right? So like the tandem solar cell which we have taken is MOS2 base and Ca3 AS I3 base. So tandem means we are taking the two different solar cells. One is top cell, second is the bottom cell. Okay, so these are top cell configuration, this is bottom cell configuration, and it can be done with the help of some numerical simulation tool like SCAPS 1D, a ForeSet is there, COMSOL multiphysics is there, and with the help of this one you can predict the efficiency, and even that can also be produced equal to the experimental result. Fine. So that can also be designed, and believe me, the device simulation is relatively easy as compared to material simulation, right? So means if you just try to analyze the complete solar cell device, it is easy as compared to DFT analysis for one particular, so means one particular layer simulation is relatively tougher as compared to complete solar cell device simulation, and it need much more time also. Okay, some other area in which we are working, so that is thermoelectricity. So if you are interested in thermoelectricity, people are not now looking on the parallel thermoelectricity, they are looking towards the perpendicular thermoelectricity. Means wherever you are having the change in the temperature gradient, right? So electricity is generated in the same direction. That is this general approach where you are having the Seebeck and the Peltier effect are there. But now, so suppose you are going to design the temperature difference in one particular area, then in the perpendicular direction, if thermoelectricity is generated, then this new type of thermoelectricity is now more famous, and based upon that we are having two effects which is coming into existence, that is anomalous hole conductivity and anomalous Nernst conductivity. Fine, so these we can simulate from theory, and we can design the experiment for that one also. Okay, so I am not going into detail of these ones. Fine, so thermoelectric energy conversion, definitely we should target thermoelectric device, photovoltaics and piezoelectric, all in our experimental lab. Fine. And so waste heat is all everywhere available from automobile factory, and if we can convert this one into useful electricity, then it will be boon for us. And this technique is foreseen for as a campaign of clean and sustainable green energy sources generation. So thermoelectric devices are eco-friendly, silent and reliable. So this is the thermoelectric figure of merit, where you are taking the help of Seebeck coefficient and electrical conductivity, thermal conductivity and temperature. So these, so a good thermoelectric material should have Seebeck coefficient up, means more, this electrical conductivity more and thermal conductivity less, right? But what happens, so why people are struggling in order to design the good thermoelectric material? Because if you just see the expression of this Seebeck coefficient and this electrical conductivity, so you are just checking that n is coming. So here n is coming in the denominator, but here n is coming in the numerator. So if you are going to increase this one, so this means this should be decreased. If you are going to increase this one, this means this should be increased. So and if you are increasing this one, this means you are decreasing this one. And if you are decreasing this one or increasing this one, this means you are decreasing this one. Okay, so means we are having some contradictory factors which limit the use of the actual value of the n. So this can be of theoretical tool, and then accordingly the experiment can be designed. Fine. Okay, so thermal conductivity, so it is having the two parts, phonon thermal conductivity and electron and hole transport conductivity, and all can be so this can be found with the help of Weizmann-Franklin law. Okay, but this thermal conductivity is controlled by the changing of the phonon conductivity because this Ke depends upon n only. Fine, because this rho, this sigma is there, n is there. But if n is decreasing, this means rho is also decreases. So this means if it is decreasing, so this means thermal conductivity is increasing. So this is our approach. We take the help of dry as well as wet lab approach. We are having the input, so we are going to, input means any particular new materials we take, we go for the geometry optimization and structure relaxation. We just check the stability is there or not, and if we know that stability is there, okay, we can directly proceed. But if it is not there, then we are having some various cross check by which we can just find whether a particular material is stable or not, whether it is formation energy, it is AIMD calculation. Okay, generally it is said that okay, DFT is a particular tool which can give you the result at 0 Kelvin. Okay, experimentalist only says in this way, okay, so whatever the results you are predicting, that is at 0 Kelvin, but our device or our material has to work at the room temperature. So how we will correlate your result with the room temperature result? So for that case, you can just check whether your material is stable up to the room temperature or not within the same phase, and that can be done with the help of AIMD calculation and phonon dispersion. You can just see. Okay, so based upon all these parameters, if the stability is coming as true, so this means you can design your experiment, and you can just check what are the thermal parameters. You can club your DFT result with the bootstrap results and with the help of perturbation theory, and it can be find that what is the relaxation time, and based upon that you can have the lattice thermal conductivity, and it can be checked with the help of BTE, right? So DFT can be clubbed with the BTE, and the thermoelectric coefficient or the ZT can be find out. An experimental approach is nothing but that similar. If you are working on this one, so precursors you just add up, and you just take this mixture on the Teflon jar, and then solvo thermal process you just take with the help of autoclave, and then filtration, drying, and powder. So then you can go for the analysis of characterization of this dry powder. So the workflow, so starting from the DFT calculation, stability testing, and then estimation of the band gap, correcting the band gap, check the thermal transport properties, and find the ZT. Okay, so if ZT is there, so this means if one particular material ZT is coming out to be optimum one, then you can design the experiment, and designing the experiment is same whatever I have explained in the previous slide. So go for the synthesis of the material, and then for the characterization we are using XRD, SEMTEM, UV spectroscopy, and so on, and then measurement of the thermoelectric properties with the help of thermal conductivity measurement system. And finally, if you are having these properties measurement, then you can find out with the help of formulas what is the power factor and the ZT, and confirmation of theoretical and experimental finding is there, right? So if you are designing the new material, so theoretical as well as experimental justification will give you more fruitful publication or patents for the novel material. Finally, so we can go for this phosphor materials, and everyone is, so this research is not new, but definitely the addition is always possible. So these days people are not focusing on rare earth doping, but they are focusing on rare earth dual doping. Fine. So we try to check the synthesis characterization as well as DFT modeling of rare earth dope, color tunable silicate and vandate phosphors for the optical properties, so that it can be used in LED or solid state lighting. So, and some research gap is there, that is limited tunable emission is there for the existing phosphor whatever have been designed, and low quantum efficiency is there at the high temperature. Okay, so pure stability for the LED, and silicate and vandate material shows high photoluminescence. So why we are focusing on these ones, and strong optical response and low cost synthesis route is there. Fine. Okay, so our motive in coming days is to design silicate and vandate phosphor, and compare comparative analysis of these two type of phos, and color tunable phenomenon in rare earth doped silicate and vandate phosphors. See, so this is the various silicate and vandate material which you can use, right? Starting from calcium, barium, so means all the series, right? And you should focus on co-dopant in such a way that you can take the terbium and europium, Ce and terbium, and in this way Dy and Eu, and this way, and depending upon this you can have a different target application. Like if you take these two dual doping, so definitely if in order to prove the new results, in order to have the new result and new phenomenon, you should go for the dual doping. And here you can just go for the white LED lighting, and if you take this one, so you can just go for the high efficiency luminous interaction, and if you take these two, you can go for adjustable broadband emission, and finally here you can target near infrared and visible up conversion. Okay, definitely up conversion is also a good thing, because many are working only on the down conversion, right? So then you can focus on this one, where you are having near infrared energy transfers, and enhanced dual band illumination is there. Fine. So all the band which are illuminated is just shown by this particular cartoon, right? So so this can be the method. So selection, first you select the material, and then you are mixing the dopant on the precursor. Go for any of these synthesis method. Go for the rectification tool, comparative study of these two, and suggest the potential application of the developed phosphor, right? So these are my target research area. So if you think that you can cover any of these research area, whatever I have mentioned, right? So you can come to our group. But for the present presentation, so this is DFT. So DFT I have tried to explain in detail. Fine. So it is energy written in terms of the electron density, and we can convert the many body problem into one body problem. So it can investigate the various physical property like structural, magnetic, and electronic properties of the molecule, material, defect, as well as nanomaterials, and it can predict various molecular properties like molecular structure, vibrational properties, ionization energy, electric and magnetic properties. And the main thing is that you have to know the exact exchange correlation functional, and if it is there, then this means you are going to produce the effective results. And these days this is very much important, because we are having HPC technology in our pair grant also. We are purchasing a new HPC server, right? So you can run your calculation on that particular HPC server also. And so HPC technology has boosted the DFT based research, because you can run the complex calculation using the HPC technology also, right? And new functions are always available for the advanced research, and in this way designing of the novel material is possible. So with this word, let me thanks all the participants for careful listening, and if you have any questions, suggestion, so all are welcome. So my student and my collaborator, teachers, all names are written here.
So can we actually predict the crystal structure if we have different orientation of this?
Definitely, you can run the different number of calculation, but your question is, I think, a little bit staggered. Why it is so? Because if you are focusing on TIC is well-known material. It is having a well-known crystal structure.
In our some cases, sometimes we get crystalline material.
Only for the crystalline material we can go for, not for the amorphous one.
Yeah.
DFT is not belonging to the amorphous material.
Yeah, we have nice pixels.
That's fine.
And but we are struggling to predict the crystal structure.
Okay.
So we have XRD and but we need to know these.
So you go for the single crystal XRD?
Single crystal is not possible. It's our material. But
It is a
microcrystalline.
Microcrystalline material.
Yeah.
Fine. Okay, so
we know the starting material. So maybe they have.
Can you give me the example? What type of materials are you designing?
Let's say it's a benzene ring with 3 functions. Okay, so it's a C.
Okay, this means it is a molecule.
Yeah. So it's a C3.
Yes, definitely.
And it is connecting with, let's say, C.
So have you checked any DFT calculation on your materials?
A lot of people are doing, but we are not getting a good collaborator, or they can do this type of simulation.
So I hope you can design these one with the help of Gaussian molecular code, right? So have you checked that one?
Not because we are not in simulation right now.
That's fine. So you are from JNU, so we can talk in this matter at a later stage, right? But with the help of Gaussian, it is possible that you can simulate the molecules. Fine. Like we design the quantum dots also. Okay. If the simulation of quantum dot is possible, so molecule is very easy. आपको और क्वेश्चन? Any other question? ठीक है. हाँ जी. Protein ligand. Yes, definitely. As this question is also similar to the previous question. So molecule. So whatever your biomolecule is there, and you have to just fix a ligand over that. So this means you are going to adsorb that one, right? So adsorption is possible, and molecular materials, molecule can be designed, and it can be simulated with the help of molecular code. So you can just focus on one particular DFT code which can simulate the molecule, and definitely biomolecule can be designed, right? So is it a molecule? If it is a molecule, it can be simulated. I am getting very much less noise. So your ligand is, you want to say that your ligand is bigger as compared to molecule, is it so? Okay. Okay. Well, we can tell it is stable or not. We cannot tell up to how much time it will be stable. So we have to just look for that one. So I'm not expert in this particular one. But definitely stability we can just tell based upon many stability check we are having. Next question, please. No. Listen. So it totally depends upon what type of materials you are having, whether you have selected the correct exchange correlation potential or not. For example, if it is D or F based material, F block element is there in your material, so then exchange correlation potential is playing a very crucial role. You may be having some advanced functional in order to design. So the proper selection of exchange correlation potential should be taken, so that you are having the result similar to the experiment one. Definitely every time we are not getting the similar result. We have to make it similar by just correcting the exchange correlation potential.
So what are the limitations of the strongly correlated system, like there are no interactions between the...
That is same, strongly correlated systems are same. These are D and F block elements. Limitation, limitation is not at the part of the thermoelectric properties. Fine. Limitation is for DFT limitation is only for the excited state properties, because DFT is giving you the exact result for the ground state properties, but not for the excited state properties. For example, the optical properties or non-linear optical properties. Here we need some more approximation or some more cross check or some more approximation or parameters we have to adopt, right? Smearing parameters we have to adopt. Next, आपका था ना क्वेश्चन? Mean silicon solar cell. Okay, so how perovskite solar cell is different from the silicon solar cell? Definitely. So efficiency point of view, almost same. You can just check NREL website efficiency. Efficiency chart is almost same. 28% is for perovskite solar cell, 28% for the perovskite solar cell. Only limitation is that it is having less lifetime as compared to silicon solar cell. So that's why people are trying to have different type of the setup, so that we can also make these solar cells stable at the level of silicon solar cell, right? So I have shown that I have taken the buffer layer, so that this remains stable for some more time. But we have to increase, this lifetime. Okay, so if it is increased, then silicon solar cell will be gone from the market. Okay, so it is predicted that up to 2035, so these will be coming into existence. Definitely these have been designed, and a roll-to-roll printing of the perovskite solar cell is there, but stability and lifetime is not more. Okay, so we have to work on that one. Hanji.
So for solar cell related things, so when we are making some doping in some semiconductors with other metals, let's say titanium is replaced by other metals. So in that, by doping, there will be change in reflectance and absorbance energy, isn't it? So, so can we do the calculations that how much doping can actually affect our...
Exactly, why not? Listen, so see, you are experimentalist. Okay, I got your point. So you are experimentalist, you know that if you are going to dope any particular material in a unit cell, so there is always a solubility limit, right? After that, you cannot add that one. Otherwise, your complete crystal structure will be different, right? So within that solubility limit, you can run any of the DFT calculation. For example, your solubility limit is 10%, so you can run the calculation from 0%, 10%, anyone, based upon what type of solar cell, what type of supercell you are taking, right?
So,
other question?
Transmit and absorbance, how you are...
That, so suppose you have got the ground state properties. Based upon that, you can just go for the optical properties, and you can just analyze, okay, for 0%, what is it is coming, for 5%, what is it coming, for 10%, what is it coming, and you can just compare. So if there is some change in the optical property, you can report, okay, so up to this point, so these are my optical properties, transmittance, whatever you're saying, and for 10% it is different, and why it is different, you can just explain based upon the density of states analysis. Okay. Okay, any other question? No? So let us close the section. So organizers are here.
Thank you, sir. Okay, thank you, sir. Thank you so much. So we are done. Time to go for lunch.